Here, we have very strong regulations, and as a result of that, the state of California is now in a position where it has to produce defensible, cost-effective, and time-sensitive approaches to establishing in-stream flows. And it's interesting, like literally written into what we call CEQA, which is the California Environmental Quality Act. It has to be based on sound science, and there has to be a transparent public process. And one of the things that happened in America is, of course, we all smoke pot. Well, not me, but a lot of Americans do. And so there's new cannabis legislation, but you know what's happening is people are going into the state and federal parks and forests in California, and they're doing these massive cannabis grows, both legally and illegally in private and public lands. And so all this water is coming out of the headwaters, going into this in a consumptive use, or being returned with really nasty pollution. The situation is so severe that in and of itself, it's become a very fast driver of environmental flow regulation needs. And so this map shows the 14 different cannabis regions that are under development for this assessment, and particularly all these coastal regions are where we're working very quickly to try to establish environmental flow requirements that will help with this problem. But looking at both what Sarah and Eric indicated, we want to go to this tier 2 where we're looking in great detail, including the ecohydraulics of any given location where somebody might be taking water out or changing the conditions. And if you divide all the streams of California into 200-meter segments, there are over 500,000 individual stream intervals that we would like to have a guideline to say, here's how much you can take. And that's a very daunting task to do. I'm going to skip over some of the stuff that we heard good context from Eric and Sarah. So the way we're approaching this is, again, putting together flow, form, and function, but trying to get down to the mechanistic level. And so within each of those cannabis regions, we're doing a comprehensive assessment that integrates all 3 of those domains. But of course, we can only do it on a relatively small sampling of sites. So any of you heard my talk before, you know I don't like statistical sampling, but at this scale, we have to apply it for now. Once we have that, then we move on to developing the archetypes. I also talked about this in my keynote on Sunday quite a bit. But Eric already showed you like what is a flow archetype in terms of those dimensionless reference hydrographs. I'm going to show you the river core archetypes, and then Sarah more or less covered the idea of trying to establish both environmental and ecological functions that have to be dealt with for any particular hydrological setting. So I think you have a pretty good sense of what those are. So what I'm going to be focusing on is how we create this channel archetype mindful of the processes. Once you have the archetypes and you start to intersect them, then the archetype becomes the basis for assigning the environmental flows to any particular 200-meter section of river in the state. Now, why are we using archetypes instead of reference reaches? Because really in the late 20th century, a lot of people were doing studies on the basis of reference reaches. The problem with the reference reach is you're saying this site is a good condition and we want to mimic that. And what people are doing is then extracting statistics from a reference site and then building flows or geomorphology to match that in a mimicry way. And it just isn't process-based and it tends not to work. The idea of an archetype is you have to go through more of the intellectual process of learning and testing to figure out what do you need to do to get the mechanisms that translate from hydrology through to the ecology with ecohydraulics as the intermediary. And I like the way that Mike had introduced that earlier this morning. So we can set up what we call design hypotheses. Your hypothesis that an environmental flow regime will lead to that outcome is a hypothesis, and you shouldn't just go from concept to then changing the flows. You need to test that. And this archetype approach is how we can do that. So I'm going to skip through this hydrological analysis because you've seen that already. So we've gone through a statistical stratification and sampling approach. So how do you take 500,000 stream segments in California and from that figure out what are the different types of streams that we have? Well, the approach that we've taken is a 3-level stratification. We begin by recognizing that most rivers can generally fall into confined, partially confined, or unconfined valleys. So we have the 3 columns here representing that typology. Then we look at sediment supply as another often overlooked driver, and we heard a question about that from Mike earlier. So then we use the universal soil loss equation for the entire state to see what are the streams that fall into a high sediment supply or a low sediment supply category. Every dot here then represents all of those for one region. So this is for the south central region along the coast. And you can see that there's massive numbers of some of these types, and then there's others that barely exist at all. So from this, we now look at the slope at any cell based on a 10 meter DEM and the contributing area to that 200 meter reach. And we then do a final classification, which is the color coding. And then for each one of these color codings, we now go out and sample 20 or so sites, which, with 5, that's about 100 sites. And we're doing about 60 sites a year, so ending at about 120 sites through this classification. So this is what we're working towards, and then that's expanded. We're doing that every region by region through the state. And our goal is to eventually cover the whole state, not just the coastal regions. So this is our sampling framework as best as we could do to be mindful of the driving processes, but still having a random component. Once we go out to the river, take your pick. Everybody's got a stream data collection approach. There's many out there. We have ones in California that ultimately begin with the EPA, but then come down to the state, and then we've modified with our own geomorphic objectives, but it's a pretty standard stuff. We then take the results of that and we put it into different approaches for statistical classification to get to stream types. So clustering is a good starting approach, but then this CART approach, with regression trees, helps you to see what is the prioritization of different variables in getting to that classification. And then you can align within the stream network to see where each 200 meter reach fits within this. And the reaches can be aggregated from 200 meters to more sensible lengths. Like, for some locations in headwaters, 200 meters could be very long. For a main stem river, 200 meters is like a tenth of a reach. The hardest part of the whole process that we're struggling with the most is that from your 120 samples per region, how do you then extrapolate to give every reach at 200 meter resolution a class? And so we're working on approaches with machine language. We have a postdoc just entirely dedicated with this, taking in all the available desktop level data and using that. Unfortunately, California does not have LiDAR for the whole state, but I think for other regions where you do have that, then that actually would really promote the ability to take a classification and have really good precision about any particular location. So from here, we have to then go to the archetyping, and to do that, we turn to the work that I did with a PhD student, Rocco Brown, called Synthetic River Valleys. So this 2014 paper presented the theory for what a synthetic river valley is and all the equations that are used to create that. And then that leads to a free open source public software in the R programming language. And there's a website called CRAN, which is this comprehensive R network. So we now have this software called River Builder, and we continue to work on it and developing it. But basically, with River Builder, you can take the data from the classification procedure you do and extract out your metrics, not only for reach scale average characteristics, but also variability metrics. So here are two very simple channel archetypes. So if you look at this aerial photo, one of the classes of the Sacramento Basin is an upland confined plain bedded channel. So there's not much floodplain here. So this is the channel archetype that's really quite similar to that. This is what it looks like on the ground. Here's a self-sustainable ripple pool in a semi-confined setting as an archetype. You can add sinuosity, it's not a problem, but in this paper we just use a simple archetype. Also, the software is more than capable of handling floodplains and terraces, and in the next version we're about to release, it is unlimited levels. So if you have an Australian macro channel with 10 terraces, then you can do that too. Although it's very rare that anyone's going to specify an environmental flow for a third level terrace. And then the last part of the archetyping that we're getting to is that we can nest in the hierarchy. You can have multiple channel types in the overall terrain, and ultimately be able to extract metrics, like if you have a LiDAR data set, to parameterize this without even having to have more channel surveys, so that your network and its, let's say, a 1 meter DEM could constrain the archetypes that are there. So once you have that, then what has to happen is you now want to get to the eco-hydraulics phase. And so we're going to perform reach scale assessments on the archetypes to then apply to get the environmental flows. So for example, if you have a geomorphic ecologic type of thing where you want to say, well, where are the locations where it's suitable for a particular in the bed activity, like maybe macrobenthic invertebrates, or looking at sediment used for spawning, then you could take your discharge time series and create an ecological function time series based on two-dimensional hydrodynamic modeling. So this is a model that shows the locations where at this flow you have suitable habitat. Relative to some ideal standard, which could be the best flow scenario or an unimpaired flow scenario, you can then average across a season to get an overall score from 0 to 1 as to how well it's performing compared to that benchmark. But like in a case where there's lots of floods, then bed occupation would be limited, so you would have a lower level. You might have another eco-geomorphic function, like then you want to have floods, have bed preparation. So at certain times of the year, okay, here are the locations that will scour and renew the bed condition. So maybe you have a time of the year when it's really good and another time of the year when it's not so good. And then you could even annualize that, because everyone wants to get to like one number. So you could say, well, what is the relative value of this season versus this season? So like an 80% weighting and a 20% weighting to get to an overall annual metric. And then this can be done as many functions that you want to look at. So the final step then is to be able to put this into an iterative process. So you have your hydrological and terrain archetypes, you do your modeling, you do your reach scale ecological performance. I don't have time to present it, but Belize is also working on a whole set of systems engineering optimization methods that would allow for optimization. So now as you adjust your flow regime incrementally, you go through a process of optimization until you get your satisfactory proposed flow regime per archetype. And then you take that, and I want to emphasize one last point. These outcomes should be guidelines. So that if you say, well, okay, here's the flow regime you should have, if the local stakeholders want to say, you know what, Greg, we have our own data, and it's better than your archetype, so forget you, then great. They can come forward with their own data and override the guideline. But the state has to have something that gets them in the room. Like I've been in meetings where the people from the state board, they don't have anything to contribute yet. This gives them something that they can say, here's what you ought to do. If you have another approach with more detail, great, bring it forward. But here's our transparent process, so it's a good starting point. So in conclusion, what do we say here? So we've seen across these three presentations that we're looking at multiple scales of resolution. We're considering hydrological, geomorphic, and ecological characterizations. We really bought into the idea of archetypes. It's still very early. Maybe 5 years from now we'll decide it was all a mistake, but I think it's a good start to see where that goes. Everything should be adjustable to the local conditions, and so that's what they can do. Thank you.